Welcome to Brain Vision.
Hi everyone, we're going to be looking at a problem that deals with thermodynamics and heat transfer. So what we're given is a pressure cooker that has a total volume of 4 liters and an operating pressure of 175 kilopascals. And in our initial state, we know that 1/2 the total volume is liquid and the remaining half is a vapor. What we're asked to solve for is the maximum rate of heat transfer that's allowed. So at the end of 1 hour, there is still liquid inside. So what we're going to do first is find the mass of water and liquid, liquid and vapor that's inside this pressure cooker. And we're actually going to be using the specific volumes of the water liquid and water vapor that are taken from table A5. So what we know is that the mass at the initial time is going to be both vapor and liquid. And we know that the definition of specific volume is volume over mass. So rearranging this equation for mass gives us mass equals total volume over specific volume, and that's exactly what we're going to use. And what we're going to say is that the mass at 1 total is going to be equal to the mass of the vapor plus the mass of the liquid. And using this relation that we have here, we can rewrite this and saying that the mass at the initial total is going to be equal to the volume of the vapor over the specific volume of the vapor, which I'm going to denote as alpha vapor, plus the total volume of the liquid over the specific volume of the liquid. And referring back to these tables, we'll see that, again, we can rewrite this equation as 1/2 total volume 1 over alpha V plus 1 over alpha L. And again, referring back to these tables, we'll see that these values for alpha V and alpha L are going to be as follows. So this equation is going to be 1/2. The volume is 4 liters, and if we're going to write that in terms of meters cubed, that's going to be 4 times 10 to the negative 3. This is going to be 1 over, so alpha V at 175 kPa is 1.0037, and alpha L is going to be 0.001057. And remember that this is equal to our M total. So when we plug this in and compute this equation, we see that M1 total is equal to 1.894 kilograms. Alright, now let's do the same thing and solve for our final mass. Now we're going to assume that our mass 2 is only going to be vapor. There's not going to be any liquid left. So that's going to be volume divided by alpha vapor, and we're operating at the same pressure, so the alpha vapor is still going to be the same of 1.0037, and the volume is going to be our 4 liters, and this is going to give us a final mass of 0.003985 kilograms. So a lot of this vapor has left the pressure cooker. So we'll see that the mass that has left is going to be equal to M1 minus M2, and this gives us a total mass out as equal to 1.890015 kg. So a very small amount. Now we're going to do an energy computation to figure out what the initial internal energy was. So we're going to denote this quantity as U1, make that big U1, is equal to the mass initial times the specific energy initial. And we can actually split this up and say this in terms of its vapor and liquid terms. So we can say Mu vapor plus Mu liquid. Now recall that we have solved for the mass before, and we can actually use the same relation of specific volume in this situation and say that this is equal to 1/2 the total volume times the specific internal energy of the vapor over specific volume of the vapor plus specific energy of the liquid over specific volume of the liquid. Now again, we can get these quantities from that table, and we'll see that this is actually equal to 926.17 kilojoules. So this is the internal energy at the beginning. Now, the rate of heat transfer is going to be determined with an energy balance, where we're going to look at the enthalpy of the vapor that has left the cooker and compare that with the energy that we had in the beginning. So remember that Q dot is equal to the change in energy over the change in time. We're just going to write that as change in energy over change in time. Now we can rewrite delta Q as M2U2 minus M1U1 plus M out H out. Now what does this mean? This means that M2U2 is the quantity of total energy that we have at the final state. And remember, we're taking out the energy from the initial state because we're trying to find the change. And then we have this energy that leaves the system, which we're also accounting for in our M out, H out term. And we're going to take all this and divide by our delta T. So we know M2U2, we know M1U1, we know M out and H out. So what we're going to do is, after we plug this in, we know our delta T to be for 1 hour, so we're just going to convert that into seconds. And we'll see that our final answer is going to be equal to 1.16375 kilowatts. And that's going to be our maximum heat transfer. And that's our final answer.